So how do we find the eigenvalues and eigenvectors of a matrix A? Well, let's recall the relationship that has to be satisfied. We have to have A times V equals lambda times V, where A is our given matrix, V is our eigenvector, and lambda is our eigenvalue. So notice the left-hand side is a matrix times a vector. The right-hand side is a number times a vector. So we want to have them match up, so we multiply this expression on the right-hand side by the identity matrix I. So I is just the identity matrix. If you're thinking about 2 by 2 matrices, it's just this matrix here, 1, 0, 0, 1. Now notice if we move all the expression here to the left-hand side, we get this. Both terms have a vector v, which we can factor out, and this just leaves this vector 0, the 0 vector. So 0 represents the 0 vector. If you're thinking about a 2 by 1 size, we're just talking about the vector 0, 0. So that's what that stands for. Now, if you haven't had linear algebra, don't worry, but what I'm about to describe is solutions to a system of algebraic equations. So if you have this system of equations, if the determinant of this matrix is not 0, then the solution of the system is v equals 0. But an eigenvector must be non-zero. So we can't allow this to happen. We must require that the determinant of a minus lambda I equals 0. So this is the equation that we solve to find the eigenvalues of A. Once we find the eigenvalues, for each eigenvalue we find, we then solve, we go back to the system of equations here, we solve that system for V, which is the eigenvector. So we solve the determinant of a minus lambda I equals to 0 to find the eigenvalues. We solve the system for each eigenvalue we find for the corresponding eigenvector. So let's run through that process. So let's find the eigenvalues and the eigenvectors of this matrix A. If you recall, if you go back to the previous session, this is the same matrix we worked with then. So the determinant of A minus lambda I, we're going to go through all the steps here. This is the matrix A minus lambda times the identity matrix. We multiply each component of the identity matrix times the number lambda, so you just get lambda on the diagonals. Term by term we subtract, so you subtract a lambda from the numbers in the original matrix. You're just subtracting lambda from the diagonal elements, and that's what you get here. All right, now the determinant, we just take this product, subtract this product. So we have minus lambda times minus 3 minus lambda minus negative 2 times 1. So we get a 3 lambda here plus lambda squared, then plus 2. And that just gives us, we write it in this order, lambda squared plus 3 lambda plus 2, which if you think back looks a lot like the characteristic equation when we're solving second order differential equations. So we take this expression, set it equal to 0, and we can factor, right? This is lambda plus 2, lambda plus 1, 2 lambda plus lambda gives you 3 lambda, 2 times 1 gives you 2. So what are the roots there? These are our eigenvalues, negative 2 and negative 1. So we found the eigenvalues. Now, for each eigenvalue, we're going to solve a minus lambda I. For this particular eigenvalue, times v equals the 0 vector. So let's write it out in terms of matrices and vectors. So here is, if you look up here, this is the matrix A minus lambda I. So we're going to plug in negative 2 for lambda. So we get the negative of negative 2, we get 1, we get negative 2, and we get minus 3 minus negative 2. when we simplify, and this is just, we're just going to call the eigenvector this vector with x sub 1 and y sub 1, and this is our 0 vector. So when you simplify, you get 2, you get 1, negative 2, and a negative 3 plus 2 gives you negative 1. And just, let's think about these as equations. That's all they are. So we have the equations 2x sub 1 plus y sub 1 equals 0, minus 2x sub 1 minus y sub 1 equals 0 from that system of equations. Now notice these equations are just constant multiples of one another, and that's always going to be true because we found the eigenvalues and the determinant of a minus lambda I is 0. So since these are the same equations, just pick one of them. So just pick one of them. So I picked the first equation. So 2x sub 1 plus y sub 1 equals 0. So all solutions to this system satisfy this equation. If I solve this for y sub 1, I find that y sub 1 is negative 2 times x sub 1. So my eigenvector has components x sub 1, y sub 1. If I select an x component, my y component has to be minus 2x sub 1. If I factor out the x sub 1, I'm left with the vector 1, negative 2. Now, there's an infinite number of eigenvectors. Any multiple, you put in a number here, multiply it by the vector, and you have an eigenvector. So let's just pick one. Let's say I let x sub 1 be 1. That makes v sub 1, 1, negative 2. And that is an eigenvector for the corresponding to the eigenvalue of negative 2. Now, we do the same thing for the eigenvalue negative 1. So again, this was the matrix A minus lambda sub 2I. That's the matrix. So I'm going to replace the lambda with negative 1. So I get the negative of negative 1. I get 1. I get negative 2. I get negative 3 minus negative 1. When I simplify those, I get 1, 1, negative 2, and negative 2. Again, just think about these as equations, a system of equations. So I have two equations and two unknowns, but the equations are really multiples of one another. So just pick one of these. It doesn't matter which one you pick. I picked the first one. So x sub 1 plus y sub 1 is 0. Solving for y sub 1, you get y sub 1 is the negative of x sub 1. So here's my eigenvector with the two components. Whatever you pick for x sub 1, the y component is going to be the negative of x sub 1 because of this. Factor out the x sub 1, I'm left with 1, negative 1. X sub 1 can be anything. Let's select 1 for it. You can pick any number except for 0. If you pick 0, you get a 0 vector, and a 0 vector is never an eigenvector. So our eigenvector is 1, negative 1. So that's the eigenvector that corresponds to the eigenvalue negative 1. Now what does this have to do with solving differential equations? This is what we found. We found this eigenvalue-eigenvector pair for these two eigenvalues. So let's suppose you were solving x prime equals ax for the matrix A that we were given earlier. Remember, we assumed that the solution looked like v e to the lambda t. So we have the v sub 1 e to the lambda sub 1t. We have v sub 2 e to the lambda sub 2t. So we're just plugging in this information from above. Now our solution, our x, is made up of two components, a little x sub t and a little y sub t. And we're finding all this information all at one time. So if you have two solutions and they happen to be linearly independent, we'll talk about that in a few days. We just take our general solution to be the linear combination of the two, just like we did with second order equations. Write down what we had from above. You can rewrite this as though you're multiplying through c sub 1 times e to the minus 2t plus c sub 2 times 1 times e to the minus t. That becomes your x. The first component. The second component is minus 2 times c sub 1 e to the minus 2t minus c sub 2 e to the minus t. That's what you get for the second component. That's the y component for your solution. So this is your solution. You could also rewrite it as a matrix times a constant vector. That's another way to rewrite this above. With a matrix we'll call phi of t, called the fundamental matrix, times a vector of constants. So we'll talk more about that in the future. But this is how you relate finding eigenvalues and eigenvectors to solving first order systems.